everybody! We just came off of a very fun, or terrible, depending on your point of view, unexpected long snowy weekend. So this module 3 features a function preparation for the finals, coming a little bit late, but hey, better late than never. Let's go ahead and put this thing together and move on from there. So the first thing that we're looking for this building block is domain, range, and interval notation. And so I want to take just a brief moment and talk about what domain, range, and interval notation are. So when we're talking about domain, you can't really see that. That's not going to work. I'll just do it right here on this. Domain. The domain is all possible x values. All possible x values. The range is all possible y values. And then interval notation is a way of talking about a range of numbers, a continuous range, so continuous, not discrete, continuous range of numbers, where what we end up having is we have the low number, comma, the high number, and then some sort of bracket or parentheses to let us know what it is. So for example, like this would be, I could say like 2 to 7 would mean all numbers from 2 to 7, including 2, that's what the bracket means, but not including 7, that's what the parenthesis means. So let's go ahead and look at what's going on here. So this wants us to identify the domain and range, whether or not it's increasing or decreasing, and to use interval notation while we do so. So the domain is going to be all possible x values. So here are our x's. So what I kind of do in my head is I look to see where is the lowest value of x. And the lowest value of x is 1, right? Because if I go to 0, there's no function there. And the highest value is 6, because if I go higher, there's no x value there. So my domain would be all x values, because it doesn't break, right? As I go from 1 to 6, like if I drag my pencil from 1 to 6, I'm always touching the black line. I'm always touching the function, okay? So that tells me that my domain goes from 1 to 6. 1 has a solid dot there, so that means 1 is included, so I do a bracket. And 6 has a solid dot there, that means 6 is included, so I do a bracket. That's my domain. I'm done. Now it wants to know my range. And so for range, I do the same thing with my y. What's the lowest value of my y? Well, it doesn't get lower than -2. -3, What's the highest value? Well, it has to go all the way to -1 here. And then as I drag my pencil up, I see that I'm constantly touching it. There's no gaps. So my lowest value is -2. My highest value is -1. -2 is a solid dot, so it's included, so I draw a bracket. -1 is a solid dot, so it's included, so I draw a bracket. And I see as I move from left to right, it's going up, so I would say this function is increasing. That's it. That's the answer. All right, let's go on to the next one. Graphing linear and exponential functions. Okay, so it wants us to graph this and then name 3 points on the line. The thing is, it's not in y equals mx plus b form, but it's close enough. We have 4 minus 3x. So the thing is, whenever we see this minus sign here, we have to assume that it's attached to the number in front of it. So instead of it -3, think of it as a -3. So really what this is, if I were to rewrite this, is g of x equals -3x plus 4. You see how I did that? I just switched those terms, and we can do that. That's the communicative property of addition, right? I know that 2 plus 4 is the same thing as 4 plus 2. I just switched the numbers around. Whoops, let's put that on the screen there, right? All I did was I switched these numbers around. Same thing as like 2 minus 4 is the same as -4 plus 2. It's commutative property of addition. So that's all we're doing here is we're taking our term, it was 4 minus 3, now I'm just rewriting it as -3x plus 4. Why? Because now it's in mx plus b form. I know that my b is 4, my m is -3. So now all I have to do is draw this. I'm going to need an intercept of 4. So I'll just draw a line like this. 1, 2, 3, 4. Okay. So that's 1 point. 1 point there is 0, 4. And then I know my slope is -3, so I go down 3 over 1. So I know the point 1, 1 is a point, and then I do it again, down 3 over 1. So that's the point 2, -2. Okay, and then I have a line, and then that's my answer. Put a bow on it. Give it to Santa. Santa works hard this time of year. Let's give him a gift. Okay? So that's all that's being asked of us, is being able to convert this into this form, name 3 points, 1, 2, 3, which is super easy if you're doing slope triangles to build the slope. I go down 3 over 1, down 3 over 1. It's called building a slope triangle. All right, let's turn the page, turn around. Building blocks, points of intersection. So what we're trying to do here is we're trying to figure out where these lines cross. We want to name the coordinate of points where the two lines intersect. So this is just y equals mx plus b, right? So I look at this, I see that my m is 3, my b is negative 4, so I go down to 4. 1, 2, 3, 4, negative 4. My m is 3, so I go up 3 over 1, up 3 over 1, up 3. And since I'm looking for a point of intersection, I'm trying to make a really good point of hitting all of those intersecting points, because it's going to make it easier assuming g of x crosses one of them. And so here's g of x. I see that my m is negative 2. I see that my b is 6. So I go up to 6. 1, 2, 3, 4, 5, 6. And I go down 2 over 1, down 2 over 1, found it, down 2 over 1, down 2 over 1 forever. But I don't really need to do that anymore because I found the point of intersection. So this is the g of x line. This is the f of x line. And I see that they cross right here, which is the point 2, comma 2. Box it up, put a bow on it. Did I do it right? Graph the system. I graphed it, yes. Name the coordinate of the point. I did. Cool, I'm done. I love being done. All right, let's move on. Ooh, I'm going to have to zoom out for this one. It's a little too big. It's too big. All right. So connecting function notation to graphing. All right. So what we're trying to do here is we're trying to connect this graph to the function notation. So what we have here is we have g of 2, and I keep saying this over and over and over and over and over and over again, but we have this italicized g in parentheses 2. This is g of x. Okay? This is the name of a function. Okay, that's not g times x. That's what the parentheses mean. If it were g times x, we would just write gx, but that's not what's going on. G is not a variable. G is the name. G is the name of the machine, the name of the function. So when we're looking at g of 2, that means what happens when we put 2 in for x into our g machine? Well, here's 1, here's 2. What happens at 2? Boink. Well, it appears to cross at 10. Is that right? 2, 1, 3. Maybe it's 9. Can't really tell. Well, I'll try to, yeah, it's 9. It's totally 9. I see it right here. I'll try to do better when I give you guys the actual test of making it a little bit more clear than this one is. But I see that it crosses at 9, so I would say g of 2, so when x is 2, my y value is 9. This one's asking when g of x is 3. So when g of x, that's my y value. So when my y value is 3, which is right here, what's my x? Well, it's 1. And then what's g of 0? Well, when x is 0, y is 1. Okay, it's just kind of like find it on the x, find it on the y. And then what's the explicit rule for g of x? Well, okay, so let's look at our table. I know when x is 0, I have 1. When x is 1, I have 3. And when x is 2, I have 9, right? So each time I'm multiplying by 3. Okay, so I know that, whoops, g of x is going to equal my n sub 0, which is 1, so I'm not even going to bother writing it, times my common ratio to the x power. Done. Right? Because that's just from explicit rules. The explicit rule being, of course, that f of x is going to equal our n sub 0 times our ratio to the x power. Right? And in this case, my ratio was 3, my n sub 0 was 1. So 1 times 3, I just left as 3 to the x power. Done. All right, moving on, moving on, moving on, moving on, moving on. I think I can zoom in for this one. Yoink. All right. Where does f of x equal g of x? So this is just asking if you know what that means. That means they're both at the same place at the same time. So where do these y values intersect? Right here when x is 2. So at the point 2, when x equals 2. Or if you wanted to get fancy, you could say the point 2 comma 5. Put a bow on it, ship it away. what is b of 4 plus g of 4? Okay, so we got to go to 4. Here's 4. Okay. F of 4, did I say b? I don't know why I was saying b. F of 4 is 7. G of 4 appears to be 6. So 7 plus 6 is 13. What is g of negative 2 minus f of negative 2? All right, g of negative 2. Negative 2 appears to be this, which is like 3. Looks like 3. That's 3. I'm going to subtract f of negative 2, which appears to be 1. So 3 minus 1 is 2. And then state the interval where g of x is greater than f of x. Well, let's look at it. When this is our y value, so where is it above f of x? Well, it's above f of x here, and then it stops here, and this is where f of x starts to be above. So if we were to go on, that'd be from negative infinity to, and then it stops where x is 2. And I'm going to say at 2 they equal each other, so it's going to be a parentheses, not a bracket, because they're not the same there. All right. Beautiful, beautiful. Okay, so I'm going to go on to Module 4 and just do this in one video. We kind of went over this in class not too long ago, but having it recorded will probably be helpful for some of you that maybe weren't here or need a quick little refresher. This one wants us to solve the inequality and graph it. So I have x plus 11 is greater than 13. So if I subtract 11 from both sides, I get x is greater than 2. I find 2 on my number line. Because it's greater than and not greater than or equal to, it's going to remain an open circle. And where is x greater than 2? Well, these are the numbers that are greater than 2. So I shade this way. And then put an arrowhead on it to show that it goes on forever. Next, determine if x equals 5 is a solution to the corresponding equation. And it says show your work. I say this so you don't just write yes, no, like prove it to me. So I'm going to plug 5 in for x. 6 times 5 minus 2 equals 4 times the quantity 5 plus 2. So 6 times 5 is 30 minus 2. 4 times 5 plus 2 is 7. 30 minus 2 is 28. 4 times 7 is 28. I have proved that they are the same thing. So that is how you would show me that you proved it. Some sort of like, yep, it works, I'm good. Another way you can do this is solving for x. So if I have 6x minus 2 equals 4 times the quantity x plus 2, we can solve for x. So I'll distribute this 4. So I have 6x minus 2 equals 4x plus 8. I'll combine my like terms by subtracting 4x from both sides, giving me 2x minus 2 equals 8. I'll isolate my x term by adding 2 to both sides, giving me 2x equals 10. And now I will isolate my variable by dividing by the coefficient of 2, so x equals 5. So yes, I've proved that x equals 5. Either of these ways proves that x equals 5. I find this way easier, but hey, you do you. Finally, solve the system using substitution. Well, if x equals 8 and all of this is going on, all I got to do is take this, plug it in for x. So that gives me 5 times 8 plus 2y equals 0. So that's going to be 40, right? 5 times 40 plus 2y, I had to think for a second, equals 0. I subtract 40 from both sides. I'm going to rewrite it up here. So I have 2y on the left equals a negative 40. I'm going to divide by 2. Y equals negative 20. I now have my y value and I have my x value. So my final answer is 8 comma negative 20. Box it up. Put a bow on it. Ship it to Santa. Have a happy holiday. Good luck on the final. Again, this is going to be what the final is, except I'm going to change the numbers around. I'm going to change the graphs just to kind of give it a fresh take. But this is going to be the very same exact format, the exact types of questions. So good luck on all of that, and study hard.